Hello everybody, thanks for tuning in to the presentation dacl10k benchmark for semantic bridge damage segmentation. In every industrialized country, the aging stock of infrastructure such as bridges is an issue. Bridges are a crucial element of the transportation infrastructure. Especially on old bridges, defects tend to appear often. These defects affect structural integrity, traffic safety and long-term durability of the building. A failure of individual structures results in enormous costs and can be dangerous. On the left side, you can see the average age of infrastructure types in blue and their minimal design lifetime in the US in 2022 in orange. Nearly all infrastructure types reach the end of their lifetime in the near future. On the right, you can see the number of bridges in need of replacement or rehabilitation in the US from 2019 to 2023 in thousands. In 2023, there are approximately 222,000 bridges in need of replacement or rehabilitation. In other words, 1 out of 3 US bridges needs to be replaced or repaired. At the current pace, it would take nearly 75 years to repair them all. Thus, frequent high-quality inspections of the infrastructure are indispensable for the ideal planning of maintenance measures, for the avoidance of unnecessary closures, to prevent the structure from abrupt failure, while at the same time we want to minimize the burden on the economy and the population because of blockings during inspections or maintenance measures. Currently practiced bridge inspections are carried out analogously by a professionally trained civil engineer. Often they have to use mobile under-bridge inspection units to access all parts of the bridge, which is displayed on the left side. Usually, the inspector observes the complete surface of the given building while documenting each defect in a damage sketch, which is displayed on the right side. After the defect detection, the inspector takes an image of the affected area and notes the damage class, size, and location in a handwritten damage sketch. This information is also called damage information. The current defect documentation, as displayed in the damage sketch, is error-prone, lengthy, and often inconsistent. So the currently practiced analog inspection process makes it difficult to guarantee frequent and detailed inspections. With dacl10k, we want to make visual bridge inspections more efficient, consistent, and safer by using computer vision for automated damage recognition. What is dacl10k dataset? dacl10k is a multi-label semantic segmentation dataset enabling the classification, measurement, and localization of defects in building components of bridges on a pixel level. To each pixel, multiple classes can be assigned. This is important as it is very common that multiple defects overlap with each other. In total, there are 18 different classes, whereas 12 of them are defects and 6 of them are bridge components. These 18 classes are pivotal in assessing the structural integrity of bridges and guiding decisions such as restoration efforts, traffic load restrictions, or even bridge closures. In this example figure, you can see several samples from the dacl10k dataset. In the top row, you can see the raw image. In the middle row, you can see the polygonal annotations, and in the bottom row, you can see the stacked masks of the classes. Specifically, I want to show you one example. Here, you can see multiple small cavities in pale purple, a hollow area which was marked with chalk in pale red, spalling in turquoise, and exposed reinforcement bars in purple, as well as rust in red. Our dataset was labeled by hand. Half of it was labeled by a professional annotation team, while the other half was labeled by 5 civil engineering students. The approach to font the classes that we want to annotate is based on several guidelines for inspections and also on the fact if these defects that are defined in the guidelines are visually distinguishable, unique in shape, and or unique in texture. Another limiting factor was during the annotation, the annotators themselves, as both groups of annotators had different backgrounds regarding the task. In order to provide baseline results, we trained 3 different architectures. The first one was DeepLab version 3+, feature pyramid network, and the segformer model. We furthermore combined 3 different encoders with DeepLab version 3+, as well as feature pyramid network. Then we also analyzed if an auxiliary loss is beneficial for performance or not, which is depicted by the check mark on the most left, in the most left column. The best performance was obtained by the feature pyramid network in combination with the efficient NetB4 encoder, resulting in a mean intersection over union of 0.41. For qualitative evaluation, we asked 5 civil engineers to annotate 4 representative images from dacl10k. We told them to annotate the images with the same granularity they would expect a software to highlight the defects. This is the practical evaluation comparing the model performance and the engineer's expectation. Here I want you to focus on 3 samples. The first 2 samples are quite easy and the last one is more complicated. The first one shows a crack. Our model does a very well prediction on the crack image. Also a good prediction can be observed for the second sample showing spalling, exposed reinforcement, rust and some cavities. Only the cavities were omitted. And the last sample, which is quite complicated also due to its low resolution, shows that our model doesn't recognize some of the defects. For example, the rest formwork, which is marked here in yellow, and the weathering, which is marked here in green. On this slide, I want to show you the class-specific and general issues that make our dataset complicated. I'm going to explain this row-wise and from left to right. We start here in the top left, where you can see challenging samples showing a crack in combination with strong weathering, here on the right, then with graffiti and a crack overlapped by vegetation. In the mid row, you can see a crack and an alligator crack in one single image. Then you can see weathering overlapping with a wet spot, and here you can see rest formwork which is covered by concrete slurry. Here you can see 3 classes that differ not a lot regarding their shape, but only regarding their texture a little. You can see here spalling, rock pocket and washout concrete corrosion. Here we can see that there is no clear border of the defect rust, and the class protective equipment here is stretched from fore to background, and here you can see many overlapping classes with partially low contrast like the border on the hatching of the hollow area in pale red, and the efflorescence in dark blue next to the bright, dry and healthy concrete surface. Here you can see different problems regarding the image quality. You can see lens flares, partial overexposure due to flashlight and sunlight. Alright, small recap. We made clear that visual inspections of bridges are important due to the aging infrastructure stock. We developed dacl10k, the first benchmark for bridge damage segmentation. dacl10k enables automating the damage recognition and documentation process, which is the basis for assessing structural integrity, traffic safety and long-term durability of bridges. Our best model shows a mean intersection over union of 41%, which was lately outperformed in our corresponding dacl challenge by approximately 10%. The challenge brings our problem to the computer vision community. It is hosted at our first workshop on vision-based structural inspections in civil engineering at WACV 2024. You are more than welcome to visit us at the workshop. Here are my references. Thank you very much for your attention. You're more than welcome to check out all the links displayed here. You can also explore the dataset on 51.